So, in last class I have discussed about the Fraunhofer diffraction, basically single slit diffraction, double slit diffraction and end slit diffraction, that is a grating diffraction. So, now I will discuss just very elementary concept of Fresnel diffraction. Fresnel diffraction, this experiment is very easy. Arrangement for experiment is not difficult one, but the mathematical treatment is slightly complicated. So, so let me just discuss the Fresnel diffraction in simple way. So, Fresnel diffraction, as I mentioned, that the diffraction effect obtained when either the source of light or the observing skin or both are at a finite distance from the diffracting aperture or obstacle, come under the classification of Fresnel diffraction, right. So, that I told earlier. So, here actually this concept of that concept of this wave front, that secondary. So, this so from wave front now we are getting these secondary wavelets. So, that concept is very important to realize the effect, to realize the Fresnel diffraction. So, if we have a source, it is a primary source. Okay. So, from this source, this spherical wavelets or wave fronts you are getting. So, now you have a aperture. Okay. You have a aperture. Now, this wave front is on this aperture. Now, here if you think that this the waves, there will be this secondary wavelets and corresponding wave front you will get. So, that way they proceed. Okay. So, on the screen, this is the screen. On the screen, what will be the effect of intensity of the light? So, that is what. So, source is at finite distance and the screen also at finite distance. So, we are interested to find out what will be the effect, what will be the intensity distribution on the screen. Okay. So, S is a small pinhole source, N M. So, that is the a small portion of wave front is allowed to pass through the aperture, and this whatever we have done. So, this basically secondary wavelets that are emitted in all direction from every point on the primary wave front. So, this red one is primary wave front. So, each point will act as a secondary source and the secondary wavelets will emit, and this will be emit in all directions. Okay. So, as if this is source, it should, so in backside also there should be the waves. So, in backside in forward direction there will be waves, that is fine. This secondary wavelets is the moving that we are telling. So, it emits wavelets in all directions. So, in backward also there should be the wave, reverse wave travelling towards the source, but experimentally it is found that no, it is not possible. So, we never get any backward wave. So, always we get forward wave. Okay. So, to encounter that part. Okay. So, whatever the experimental observation to take into account that this experimental observation. So, we have to consider this one factor that is called obliquity factor. So, the amplitude of the wavelets, whatever it is reaching on the screen. So, it will depend on the direction of the wavelets. Okay. If this angle is theta, so this amplitude will be modified with this obliquity factor. That factor, if I tell k theta, so that is equal to half 1 plus cos theta. That means, if theta is 90 degree, so along this direction 90 degree, theta is 90 degree. Okay. So, this factor will be half, that means light going in this direction, the intensity of that light will be just 1/4, whatever the light is going this side. Okay. Wavelets are going this side, theta equal to 0. So, whatever the intensity will be there, amplitude will be there. So, this side amplitude will be half of that. Okay. So, this obliquity factor is multiplied with the amplitude, and that is why amplitude will not be same in all directions. So, it will depend on the theta. So, that is the obliquity factor that was taken into account. So, diffraction by a circular aperture, that means you have a source in finite distance. Okay. So, from that source light is coming and falling on this screen where there is a circular aperture. So, or obstacle where there is a circular aperture. So, light will pass to this circular aperture. Okay. So, then the screen is placed at a finite distance here. So, on the screen, due to circular aperture, so on the screen we will get this type of intensity distribution. So, basically we will get ring pattern, or circular diffraction pattern on the screen. Okay. So, now how it is formed? As well as when diffraction by a circular obstacle, so this kind of things. Okay. So, light should not pass along this direction, right. So, we should not get any. So, this the basically is the normal to the center of the circular aperture. Okay. So, what will be the intensity at this point, So, these are the center, it is this point is on the axis passing through the center. So, other points we tell the off center. Okay. So, here I understand this at the center. So, light should be there, but it is a dark bright. So, it can be at this center, it can be center one, it can be dark, it can be bright. So, depend on some factor. So, sometimes we can see dark if screen distance if we change. So, at some distance we are getting dark, at some distance we are getting bright. Okay. And then alternate one we are getting. So, in circular obstacle, so at the center here, so this dotted line, actually this the passing is the normal to the center of this disc. Okay. And it is on the screen at this point. Okay. Axis on this, basically we tell the axis passing through the center. So, at the center here, so we will get also taking this one as a center. So, we will get circular diffraction pattern, and in this case surprisingly this at the center all the time it is bright. It does not matter you are changing the skin distance, but all the time it will be bright. So, it is supposed to be dark because there should not be any light directly passing. So, light are coming from this other part of the circular obstacle. So, but here all the time it is bright, okay, on the skin. So, this type of fringe we get, basically diffraction pattern we get. So, these are the due to the Fresnel diffraction. So, how it happens? So, to understand that one, so basically Fresnel itself he has developed constructed Fresnel's half period zones. So, because if using the Fresnel half period zone, we can from that concept, from that approach we can basically explain this Fresnel that diffraction pattern. So, just let me discuss the this what is that Fresnel half period zones. Okay. So, Fresnel half period zone is basically if you take a, so from the source spherical wavelets are spherical wavefronts are coming. So, this is a portion of this on that spherical wavefront. Okay. Now, from point P, at point P, so this is the wavefront. Now, at a point P you want to see the effect of this wavefront. Okay. So, now from point P if you just draw a normal on the wavefront, on this wavefront. Okay. So, that O basically on the wavefront is the foot of the perpendicular on the wavefront from P. Okay. So, now around P on the wavefront a series of circle is drawn on wavefront such that each circle is a half wavelength further from P and distance from P are B plus lambda by 2, B plus 2 lambda by 2, B plus 3 lambda by 2. What is the B? So, B is basically OP, and now if you draw the circles, okay, in such a way. So, each circle, so this circle, distance of this circle is basically, so distance of the center from P is B. So, then distance of this circle is from P is basically B plus lambda by 2, half wavelength more. So, next circle that is the B plus 2 into lambda by 2. So, 3 into lambda by 2. So, that way if you draw circles, and the distance of these circles from this O, along the arc are say S1, S2, S3 etc. this SM for mth zone. So, these zones, this area between two circle, between these two circles. So, that is basically we tell zone, and if you just proceed. So, this area, so this is the area, and then next area, between these two circles, this next area. So, these are called basically zones, and we tell half period zones, this area. So, we tell these half period zones because there, so light will come from these zones to P. So, their path length difference will be from each other, from one after another. So, whatever light coming from here, so whatever from this region, so from next region, so this path difference will be lambda by 2. From the next one, it will be between these two successive 2, it will be lambda by 2, all the time lambda by 2. Okay. So, from the beginning, so lambda by 2, then 2 lambda means lambda, 3 lambda by 2, 4 lambda by 2, etc. So, this path difference between two successive areas, all the time it will be lambda by 2. Okay. So, that is why it is called half period zone, it is called Fresnel's half period zones. So, now from this construction we would like to find out this, what is the area. So, area depends on what. So, that we would like to see, or what is the path difference with respect to OP, what is the path difference with S1P, S2P, S3P, SMP. So, let us see. So, area of the zone, to find out area of the zone. So, basically this is the wavefront block 1, we consider the block 1 the wavefront. Okay. And so this is A source, from A source this lighter spherical this wavefront is coming. Okay. Now, from this center of this wavefront, if this is A, this distance is A, this distance is A, that means this HQ, this distance also A, right. So, now if you draw a circle from P, if you draw a circle, it is okay. So, basically it is touching, it's a so wavefront is basically, this wavefront is basically tangent to this at this point. Okay. So, then what will happen? This is the screen distance, this is the screen distance from this wavefront. Okay. If it is B, and this is the source distance if it is A. Okay. So, actually light from H, one light from this wavefront. Okay. So, these are coming at P. Another light, so this, if you consider this point on the wavefront. Okay. So, this light is basically coming from H, and then from this wavefront is light is reaching here at P. So, what is the path difference between these two? And if say so this A and B is very large compared to the S. What is the S? From the center, this basically radius of the concentric circle drawn on the, it is it's a more or less we can say the radius, but it is difficult to say the radius. So, it is along the arc basically what are the distance from the center. So, that is so if it is not plane wave, so it is difficult to say, but this okay, more or less you can say that is the radius of this circle. So, here in general, so this is the first this point Q, it is the for first circle or first zone plate, half period zone, or second, or whatever in general. So, that is why we have considered S. So, now to find out it path difference, so if you just draw a normal from Q, that is a normal on this HP. So, that is the Q dash, and from this point it is the R dash, it is the R point R, and this is the R dash. So, basically if you so what you can see, this is A, this is also A. Okay. So, this path and this path is same, And now in this case you see this path, this is B and this is B, up to R it is B. Okay. Now additional path is basically QR, you know, additional path is QR. Now this QR, if you draw the normal from here, so QR is basically that path difference, that is nothing but O Q dash plus O R dash, O Q dash plus O R dash. Okay. So path difference between these two, one is passing through the center and another is passing through the say through the edge of the to the one edge of the half period zone. So or middle of the half period zone. So what will be the then path difference between these two area? So that's that is del. So this so this you can find out. So from here you can write HQ square equal to HQ dash square plus QQ dash square. Okay. So so from here you can find out OQ dash equal to A square by 2A. So approximation we have taken that this S is basically is here that QO OQ is a very small compared to A and B. So similarly for this other part also you will get O R dash equal to A square by 2B. So del path difference basically you are getting from these two contribution, this plus this, A plus B divided by 2AB A square. So so this also one can write that 1 by A plus 1 by B, half 1 by A plus 1 by B into A square. So in that form also one can write. So if this is the path difference, so for mth Fresnel zone, so this S we can write SM is the radius of that from the center. Okay, from the center this SM is the radius and the path difference will be. So if it is mth one, so this here is lambda this B plus m into lambda by 2. Okay. So this one will be m into lambda by 2. Okay. So path difference basically this del is the basically m lambda by 2 equal to del, and the del, what is del that we have calculated, it depends on A, B and yes, it depends on B, A and which zone we are considering, of course. So for mth Fresnel zone we can write this. Okay. So from here that so this is, so this SM we can find, SM square you can find out from here, SM square you can find out. So area will be this is the radius, SM is the radius. So pi SM square, that will be area of the for that circle, and S m minus 1. So we put the just m minus 1 circle. So that area will be pi S m minus 1 square, right. So difference of this will give the area between these two, m minus 1 and mth circle. So area between these two. So area of any zone of these two zone basically we can write that area. So, this we have written capital S for mth zone. So, this difference between these two successive these areas. So, from here you can find out that S m equal to A by A plus B pi B lambda. Okay. So, one interesting thing you can see that although we have found the area of the mth zone, but this is independent of M. So, that is why this can be the area of any zone. So, this zone or area of each zone is approximately same, because some approximation we have taken for this. So, that is why this actually area of each zone is approximately same, area of each zone is approximately same and independent of M. So, Fresnel's zone we constructed, Fresnel's constructed. So, this in such a way from each zone whatever light will come at P, P is the point on the axis passing through the center of the wave front. So, light will come from each zone. So, their wavelength difference will, path difference will be lambda by 2. Okay. Between successive zones, path difference always it will be lambda by 2. Okay. So, now then what will be the intensity or the amplitude at point P? So, that is what we are interested to know, then you will know the intensity. So, amplitude at P due to whole wave front. So, we can write this total amplitude at P is A equal to A1 from first zone, then second zone, second half period zone. So, it will be just phase difference is just opposite, okay, pi phase difference or lambda by 2 path difference. So, it will be, so then A1 minus A2, okay, opposite phase it will come with opposite phase. So, minus A2 plus A3 minus A4 etc. So, minus 1 to the power m A to the power m, not A to the power m. So, for mth zone, this A is amplitude from the mth zone. Okay. So, if m is odd, so this we can rearrange like this. M is odd, so if it is 3 A1 A2 A3, so I can write A1 by 2 plus A1 by 2 minus A2 A3 plus A3 by 2 plus A3 by 2. Okay. So, this term is going extra A3 by 2. So, if it is odd, then this A m by 2 is going to be extra. Okay. So, here what is telling this half of the amplitude from the first zone and half of the amplitude from the second zone. So, on the average these two will be equal to the amplitude from the second zone. So, that is the concept, because amplitude from each zone they are not same. Why they are not same? Because of obliquity factor. So, they will decrease basically. So, that is why here we have taken average this way, so that this will be cancelled. So, only left A1 by 2 plus AM by 2. Similarly, if M is even, then you can show that same way of rearranging that one. So, that A will be A1 by 2 minus AM by 2. Actually, due to obliquity factor, if M is very large, so this amplitude AM will be very small, negligible compared to A1 from first zone. So, that is why this A amplitude due to the whole wave front at P where the amplitude. So, this amplitude is just half of the for amplitude for the first zone, is just half of it will be the resultant amplitude at P, and corresponding intensity will be just square of it. Okay. So, at P what will be the intensity? So, just is the it's the intensity is there, is not because of whole wave front, for whole wave front if everything is added, then what will happen? A1 plus A2 plus A3 both are all are equal. So, that will be MA. Okay. So, M square A square, that will be the intensity. Okay. But most of them are cancelled. So, intensity will resolve. So, at point P at the center, so off center point if we considered, so from there again you have to draw a normal on the wave front, find out the footprint foot of the normal, and you have to see that how many with respect how many. So, you have to again find out the zones, half period zones, and how many they are contributing there. So, so that way for different points one can find out the intensity distribution on the screen. So, these just preliminary, there are more complicated examples and there are other ways to calculate. So, this is the one way to calculate, so that for simple case we use this one. So, one of the application is basically zone plate. So, just that I will discuss and complete it. Zone plate. So, now from Fresnel's half period zone we have seen, and from there this we have seen the expression m lambda by 2 equal to what we have seen, S m square 2 AB divided by A plus B. So, that we can write basically in this way 1 by A plus 1 by E. Okay. Now, if you imagine that, so for a given A B, A is basically from obstacle source distance, B is basically from obstacle this screen distance, image distance, and this lambda for a given these 3 quantity parameter, the zone area. Okay. So, zone must have this Sm equal to, so these are constant, then these are constant. So, Sm square will be is proportional to m, right. So, that is why, so for a particular A, B and lambda we can construct zones. Okay. It is a radius, it is Sm is this that concentric circle we are doing. So, these are radius. Okay. So, that radius if we take, that is square root of m. Okay. So, means first zone is the, if you take 1, then second zone this square root of 2, square root of 3, square root of 4, square root of 5, okay, in some unit length unit. If you take this radius and on a plate, you take a plane of paper and you draw the concentric circle with this radius 1.1, root 2, root 3, root 4, okay, then you will get basically the you are constructing the zone plate, you are constructing the Fresnel's half period zones. Okay. Now, either odd zones or even zones, if you just make opaque, okay, use the black ink and just close that odd zones or even zones, either odd zones or even zones, and other are transparent. Okay. Then what will happen? Then A1 minus A2 plus A3 minus A4. So, whatever the opposite phase these wavelets are coming, so now they are not coming, all are coming, those are in phase, okay, coming from first zones, then third zones, then fifth zones, or other way second zones or fourth zones or sixth zones. Okay. So, all amplitude will be added at P, A1 plus A3 plus A5, all will be added in P. So, you will get huge intensity at the center, you will get huge intensity at the center as convex lens does. So, if you put light on a convex lens, all light will be concentrated at the focal point, high in very huge intensity will get at the focal point. So, that is why if you see this one, this relation A 1 by A plus 1 by B equal to m lambda by S m square, as if this is 1 by F. So, 1 by V minus or plus 1 by U equal to 1 by F. V and U nothing but the source distance and object distance and image distance. So, here A and B source distance and screen distance. Okay. So, this is like just focal point. It's so depending on this, you see radius of this SM, no. Okay. Choosing this one. So, you can basically it is just like convex lens of different focal length you can produce. So, this way we have the device we fabricate. So, that is called zone plate. Okay. Alternate zones are blocked and other zones are open, opaque, transparent. So, light will pass to that and you will get the action like convex lens. Okay. So, I think I will not discuss more on this Fresnel's diffraction. In laboratory, so, we will try to demonstrate one experiment based on the zone plate. Okay. So, thank you for your attention.